Energy resources, the scientific and technological challenge of the 21st century. Our objective here is to provide a description of the present energy challenges. Energy may be the most important scientific and technological challenge of the 21st century. Energy is essential to modern life. Without it, many billions of people would be left cold and hungry, and long-distance communications would be extremely difficult. In most places, economic growth and energy demand are closely correlated. The availability and use of energy, especially electricity, are sometimes considered a direct measure of the economic well-being of a society. Here are some of the key references used to develop these lectures. Here are our learning objectives for this lecture. Once you finish this lecture, you should have an understanding of the differences between primary sources of energy and secondary sources of energy. You should also have an understanding of the differences between renewable sources of energy and non-renewable sources of energy. At the end of this lecture, you should be able to answer this question: why is energy a major challenge of our time despite the fact that we have many sources of energy? Here is the plan we will follow. We will start by answering the question, what is energy? Energy is defined as the capacity for action or the performance of work. According to the first law of thermodynamics, that is, the energy conservation law, energy can be neither created nor destroyed, but it can be transformed into different states or forms. Matter is a special form of energy and is included in the energy conservation law. Energy that is waiting to do work, that is, energy that has the potential for work, is called potential energy. The unit of measurement used to express the heat contained in energy resources is called a British thermal unit, or BTU. The BTU equals about 1,055 joules. The unit MBTU has 1,000 BTU. MMBTU represents 1 million BTU, and quad represents 10 to the 15th power BTU. The United States uses an enormous amount of energy, more than 1 quad of energy every 3.7 days in 2007. The forms of energy include heat, light, microwaves, and electricity. Potential energy stored in a body, for example, the gravitational field at an elevation. Kinetic energy of a moving object. Energy associated with the chemical bonds that hold atoms and molecules together. Nuclear energy created by transforming matter into energy. All of these represent other forms of energy. One form of energy, which did not make the list above, is food. In fact, food, the main source of energy that fuels our bodies, is one of our most important sources of energy. Electrical energy is used to power lights, computers, and industries. Fossil fuels power our cars, boats, and airplanes. We consume energy directly through transportation and household uses, and indirectly through goods that require energy in their production. The primary sources of energy include fossil fuels such as natural gas, oil, and coal, and to a lesser extent, nuclear energy through fission of radioactive elements and through rivers that provide hydroelectricity. As we discussed in previous classes, the Earth can be divided into 4 spheres. These spheres are atmosphere, hydrosphere, biosphere, and lithosphere. As you can see here, the atmosphere is associated with wind and solar energy. The hydrosphere is associated with hydroelectricity. The biosphere is associated with biomass. The lithosphere is associated with oil, gas, including gas hydrate, which is oil and gas in solid forms, coal, uranium, geothermal, and more. All of these spheres are interconnected, with biosphere at the center. Solar energy is essential to the function of each of these spheres and for the entire system. These connectivities are also central to the formation and description of energy resources. For example, the sun is central to the solar energy, to photosynthesis, and more. Photosynthesis is a process used by plants and other organisms to convert light energy, normally from the sun, into chemical energy that can be later released to fuel the organism's activities. Evaporation occurs when the physical state of water is changed from a liquid state to a gaseous state. Energy resources are generally grouped into renewable and non-renewable types. Renewable resources can be replenished over a short period, say months, years, or decades. Energy from the sun, flowing water, and wind are renewable. Geothermal and biomass are also renewable energy resources. Non-renewable energy resources such as coal, oil, and natural gas continue to be formed in Earth, but the process that creates them can take millions of years. Nuclear energy is also a non-renewable energy resource. These energy resources are also known as primary energy. In other words, primary energy is found in nature, but has not been subjected to any conversion or transformation process. Alternative energy is any energy that is produced from sources other than fossil fuels. Secondary energy sources, also referred to as energy carriers, are the more convenient forms of energy that can directly be used by society, such as electrical energy, heating, refined fuels, and synthetic fuels. Unlike the primary sources, secondary energy sources, such as electricity, are not classified as renewable or non-renewable. Electricity cannot be mined from the ground like coal or captured from moving air like wind, so it is called a secondary source of energy, meaning that it is derived from coal and wind, as well as other primary sources, including natural gas, nuclear reactions, and hydropower. Let's now describe primary energy sources in more detail. We will start with non-renewables. We will describe three non-renewable energy resources: oil and gas, coal, and nuclear. We will start with oil and gas. In this lecture, petroleum is defined as crude oil and natural gas plant liquids. Petroleum, or oil and gas, is a naturally occurring flammable liquid. It is formed from organic matter, tiny plants, algae, and bacteria, or plankton, that lived in the ocean millions and millions of years ago. As living organisms, they absorbed energy from the sun, which was stored as carbon molecules in their bodies. When they died, they sank to the bottom. Vast quantities of these remains long ago settled on the bottoms of lakes and seas, mixing with sediments and being buried under special anoxic conditions. As more layers settled, intense heat and pressure build up in the lower regions. Burial, and thus the heating of such organic matter, induces reactions leading to the generation of gas, then oil and gas, at 110 degrees to 140 degrees Celsius, and finally to gas alone, at 140 degrees to 250 degrees Celsius, as the temperature and the residence time at high temperatures increased. By the way, anoxic conditions will occur if the rate of oxidation of organic matter by bacteria is greater than the supply of dissolved oxygen. Through billions of years of biogenic and thermogenic processes, the Earth has naturally produced large accumulations of oil and gas. In only 100 years, humans used more than half of all the oil on the planet. Oil that took billions of years to produce and that were the result of climatic conditions that existed at only one time in the Earth's 4 billion year history. Let me repeat this. Through billions of years of biogenic and thermogenic processes, the Earth has naturally produced large accumulations of oil and gas. In only 100 years, humans used more than half of all the oil on the planet. Oil that took billions of years to produce and that were the result of climatic conditions that existed at only one time in the Earth's 4 billion year history. Yet society's demand for oil has not stopped increasing. Oil is too important to modern life. 80 to 95% of all transport is fueled by oil products. 50 to 70% of all oil is used for transportation. All petrochemicals are produced from oil. 99% of all lubrication is done with oil products. 95% of all goods in shops arrive by oil-powered transportation. And 99% of our food involves oil or gas for fertilizers, agrochemicals, tilling, cultivation, and transport. Let's now talk about the next non-renewable energy, which is coal. Coal is another carbon-based resource that provides energy and the raw materials to make other products. Coal is formed from buried and compacted plants. There are different types of coal. We have peat, which is 50% carbon, lignite, which is 70% carbon, bituminous, which is 85% carbon, and anthracite, which is 95% carbon. The organic materials in coal start as compressed and partially decomposed plant matter, including peat. Once dried, peat can be burned. Lignite, or brown coal, is a brown, not very dense coal. Bituminous coal, or soft coal, is fairly dense. Anthracite, or hard coal, is dense and shiny and has the highest quality. Coal is mined through surface mining and subsurface mining. In surface mining, coal is mined in large open pits where coal layers lie close to the surface. Miners remove one long strip at a time. The entire strip mining operation moves across coal-bearing areas, and it may affect very large areas because of the ways in which they are mined, transported, and processed. Two important notions in surface mining are overburden and open pit. Overburden is soil and rock removed from stripping away using mechanized equipment. An open pit is a large hole that is dug to remove deposits of mineral ores in sandstone, gravel, and stone. Huge shovels remove overlying materials called waste to expose the coal. These wastes are stored or used to fill parts of the pit where coal has already been removed. Let us now turn to subsurface mining. The better coal varieties, bituminous and anthracite, are mined underground, for example, in the Appalachian region of the U.S. In underground mines, miners remove relatively thin layers called coal seams and then haul them to the surface, either through vertical mine shafts or up gently sloping roadways. Underground mining is more labor-intensive, more dangerous, and more expensive than strip mining. Coal is the world's most abundant fossil fuel and a major fuel used for electricity generation worldwide. The coal is crushed, stockpiled, and then transported to power plants, steel mills, and other sites. Power plants burn the coal to generate enough heat to convert water to steam, which then turns the turbines inside electrical generators. The electricity is immediately sent on its way since it cannot be stored. Coal can also be converted to fuels and can be gasified to create natural gas for power plants, but the resulting amounts are small. In summary, coal is a carbon-based resource that provides energy and the raw materials to make other products. Coal is the largest primary source of energy used for electricity generation worldwide, as you can see in this chart. Leading world producers of coal in 2014 were China at 45.5%, the United States at 11.6%, India at 7.8%, Indonesia at 8.3%, Australia at 5.9%, Russia at 4.4%, and South Africa at 3.3%. And again, in this chart, you can see where the world gets its electricity from. Now we will discuss the last non-renewable energy, called nuclear power. The notion of nuclear fission and neutron poison, in addition to the basic description of atoms, is the cornerstone of nuclear energy. The atom is a basic unit of matter that consists of a dense central nucleus surrounded by a cloud of negatively charged electrons. The atomic nucleus contains a mix of protons and neutrons. A group of atoms can remain bound to each other, forming a molecule. Chemical reactions involve outer electrons. Nuclear reactions involve changes in nuclei. Nuclear reactions produce enormous energy that can be harnessed to power electrical generators. Protons are positively charged particles which are located in the nucleus. Neutrons are neutrally charged particles which are located in the nucleus. Electrons are negatively charged particles which revolve around the nucleus. Nucleus is the center of an atom. This consists of protons and neutrons. An atom is classified according to the number of protons and neutrons in its nucleus. The number of protons determines the chemical element, and the number of neutrons determines the isotope of the element. Note that the atomic number is the number of protons. The atomic weight is the number of protons plus the number of neutrons. Nuclear fission is the process of splitting a nucleus into two nuclei with smaller masses. Fission means to divide. It splits into two parts, breaking apart nuclei. Only large nuclei, usually uranium-235 or plutonium-239, with atomic numbers above 90 can undergo fission. Uranium-235 has 92 protons and 143 neutrons. Products of fission reaction usually include 2 or 3 individual neutrons. The total mass of the product is somewhat less than the mass of uranium-235. A neutron poison, also called a neutron absorber or a nuclear poison, is a substance with a large neutron absorption cross-section used in applications, such as nuclear reactors, when absorbing neutrons is a desirable effect. Notice that neutron-absorbing materials, also called poisons, are intentionally inserted into some types of reactors in order to lower the high reactivity of their initial fresh fuel load. Large accumulations of uranium are associated with granite, some sedimentary rocks, and groundwater. Most of the large accumulations of uranium are found in Australia, about 45%, Kazakhstan, about 15%, Canada, about 14%, and Southern Africa, about 10%. Nuclear fission is the process of splitting a nucleus into two nuclei with smaller masses. Uranium was discovered in 1789 by Martin Klaproth, a German chemist. It is generally recovered through in situ mining. Uranium has two major isotopes, uranium-238, which is generally not fissionable, and uranium-235, which is fissionable. This is the most common nuclear fuel. When uranium is bombarded by neutrons and by a non-fission reaction, it is turned into plutonium-239, which is fissile. Plutonium-239 fissions are like uranium-235 and also yield a lot of energy. A chain reaction is an ongoing series of fission reactions. Billions of reactions occur each second in a chain reaction. On Earth, nuclear fission reactions take place in nuclear reactors, which use controlled chain reactions to generate electricity. The nuclear chain reaction can be controlled by using neutron poisons to change the portion of neutrons that will go on to cause more fissions. Nuclear reactors generally have automatic and manual systems to shut the fission reaction down if unsafe conditions are detected. Let's repeat this. The nuclear chain reaction can be controlled by using neutron poisons to change the portion of neutrons that will go on to cause more fissions. Nuclear reactors generally have automatic and manual systems to shut the fission reaction down if unsafe conditions are detected. The controlled or nuclear fission chain reaction produces heat, which boils water, which produces steam, which drives a turbine, which then generates electricity. Most nuclear reactors are light water reactors, or LWR, meaning that they are cooled and moderated with ordinary water. Let's repeat this again. Most nuclear reactors are light water reactors, meaning they are cooled and moderated with ordinary water. Also, the controlled nuclear fission chain reaction produces heat, which boils water, which produces steam, which drives a turbine, which then generates electricity. In nuclear reactors, the heat generated by the reaction is used to produce steam that turns into a turbine connected to a generator. After about 5% of a nuclear fuel rod has reacted inside a nuclear reactor, that rod is no longer able to be used as fuel due to the buildup of fission products. Fermi used uranium to produce the first controlled chain reaction. Uncontrolled chain reactions take place during the explosion of an atomic bomb. Uncontrolled fission chain reactions powered the first atomic bomb, which was 21 kilotons. Let us return to controlled fission reactions in nuclear powers. Nuclear power plants provided 10.9% of the world's electricity production in 2012. In 2014, 13 countries relied on nuclear energy to supply at least 1/4 of their total electricity. In 2014, nuclear power provided 77% of France's electricity, 38% of Switzerland's electricity, and 19% of the US's electricity. These are interesting and important numbers we just shared. In other words, nuclear power represents an important source of the world electricity. However, nuclear power is expensive. It has a low net energy yield and creates long-lived radioactive waste. It is vulnerable to sabotage, and there is a potential for spreading nuclear weapons technology. There can be a loss of reactor control. Plant safety is a major concern, especially the threat of terrorism. Nuclear waste is highly radioactive and must be stored safely for 10,000 to 240,000 years. Ideas for dealing with nuclear waste generally include underground burial of waste in subduction zones and converting waste into harmless particles that can be disposed of in space. The viability of these solutions has not yet been proven. Moreover, although rare, nuclear accidents are very costly in human life and to the biosphere in general. There have been only 3 nuclear accidents so far. On March 28, 1979, in 3 Mile Island, Pennsylvania, in the U.S., a pump that circulates water to a cooling system in the nuclear reactor failed. Without cool water, the heat generated in the reactor rose above the boiling point, and the pressure inside the reactor climbed to 2,350 psi. Radioactive particles were then vented into the air. 2 days later, a sudden and uncontrolled burst of radiation came from 3 Mile Island. Approximately 200,000 people chose to evacuate, but no deaths were reported. On April 26, 1986, in Chernobyl, Ukraine, a series of explosions caused the roof of a nuclear reactor building to blow off, and a huge radioactive cloud spread over many countries and eventually the world. The estimated death toll was 212,000, and there were huge long-term effects on human health, the water supply, and agriculture. On March 11, 2011, in Sendai, Japan, ground shaking caused by an 8.9 magnitude earthquake and a subsequent tsunami damaged the 2 Fukushima nuclear power plants, that's Fukushima Daiichi and Fukushima Daini, and caused explosions. Radiation levels rose to 1,000 times normal levels. More than 10,000 people died in the combined earthquake, tsunami, and nuclear accident. Note that there are 2 types of nuclear reactions, fusion and fission. In other words, we have fusion in addition to fission. Nuclear fusion is the combining of 2 nuclei with low masses to form one nucleus of a larger mass, forming or adding to nuclei. Nuclear fusion reactions are also called thermonuclear reactions. Fusion reactions exist in stars. Our sun is a good example of a thermonuclear or fusion reaction. It is extremely difficult to create fusion reactions on Earth, since they need temperatures above 1 million degrees Celsius in order to take place. Nuclear fusion produces less nuclear waste than nuclear fission, and the materials are easier to obtain. Nuclear fusion reactions have the potential to be safer and generate less radioactive waste than fission. These reactions have yet to be created on a scale that can be used in a functional power plant. Fusion power has been under intense theoretical and experimental investigation since the 1950s. Uranium-235 contains 8 more times the energy of all the other natural energy sources combined. 1 kilogram of uranium can produce 50,000 kilowatts per hour of electricity, whereas 1 kilogram of coal produces only 3 kilowatts per hour. Nuclear power has a low environmental impact and a very low accident risk, but high costs, a low net energy yield, long-lived radioactive waste, vulnerability to sabotage, and the potential for spreading nuclear weapons technology have limited its use. It is the slowest growing energy source and is expected to decline more. No plants have been built since 1978 in the United States. In 2012, Germany and Switzerland started phasing out their nuclear power. This figure shows that proven reserves of uranium have peaked and are going down rapidly. Current nuclear plants consume around 1.75% of estimated high-grade uranium reserves per year. At this rate, the present resources would last 57 years. In summary, nuclear power has a low environmental impact and a very low risk of accidents, but they have high costs. long-lived radioactive waste, and potential catastrophic effects in the case of an accident. Yet it still provides about 11% of the world's energy, despite the fact that it is the slowest growing energy source. We have now concluded our discussion of what energy is and the descriptions of non-renewable energy sources. When we return, we will discuss about renewable resources and the energy challenges.